So today I'm going to talk about our work on deriving a new radiative transfer framework for non-exponential media. And the authors of this paper are myself, Benedict Bitterli, Renat Ravikandran, Thomas Müller, Magnus Wenninge, Jan Nowak, Steve Marshner, and Wojciech Jarosz. And the institutions are Dartmouth College, ETH Zurich, Disney Research, Pixar Animation Studios, and Cornell University. So this paper is about rendering participating media. And these participating media are all around us, ranging from atmospheric effects such as clouds to everyday effects such as foods and juices, or ice and snow, or even more exotic things such as interstellar clouds. But no matter the material, if we look at these media very closely, we could see that they're made out of lots and lots of scattering particles. Now, when we render one of these media, one of the key properties that we're interested in is something called the transmittance, which is the average fraction of light that is transmitted through a stretch of medium. Now, for any particular arrangement of these scattering particles, we can see that the transmittance is quite a complicated function because it relies on the mutual shadowing of the different particles, which makes it quite complicated to compute or represent. However, in practice, we're not interested in any particular arrangement of particles, but rather we think of these particles as the result of a random process. So in other words, these particles are distributed randomly. So what we really want is kind of the average transmittance over all possible arrangements of these particles. Or in other words, we want the expected value over all arrangements. And so if we take this expected value, then we get a transmittance curve that is a lot smoother and a lot easier to represent and more closely represents what we're after. Now, to describe interactions of light with participating media, we need to go into radiative transfer theory. And so a lot of work has been done in this field, and one particularly popular book in this field is that on radiative transfer by Chandrasekhar. Now, one of the fundamental assumptions made by radiative transfer theory is that the positions of the particles are independent of each other. So no particle knows about any other particle. And so one of the things that this buys us is that the transmittance for the case of independent particles reduces to an exponential. And this is a very useful property that is quite handy in practice. But of course, whenever we make such an assumption, we have to ask the question of how accurate is this really, or how closely does this model real participating media? And it turns out that media in reality usually do show some kind of correlation. The particles are not distributed independently. And so just an example of this is that physical particles have a size, a physical extent, and so they can't get arbitrarily close to each other. And so clearly there's some interdependence between the particle positions. And beyond that, there's quite a bit of research that shows that there are electrostatic forces, or even van der Waals forces, between these particles that cause them to repel or attract each other. And so maybe a more accurate picture of the particle distribution is something like this, where the particles don't like to be near each other. For the specific case of clouds, there's also been research showing that the distribution of water droplets in clouds is better modeled by something like this, where we have a very patchy appearance, and these interactions or correlations between particles exist on very large scales, so from meters up to kilometers. And so a more accurate picture of the particle distribution is maybe something like this, where we have these large voids between particles, but also large clusters of droplets. So I've made the case for why particles are correlated in nature. And of course, the next question is, does this matter? Does this affect the properties of the medium, such as the transmittance? And to show this, we've done a little numerical experiment where we've actually instantiated particle distributions that follow these different types of correlations. And then we've numerically measured the transmittance through these media. And so here on the left-hand side, we have a classical independent particle distribution. And if we numerically measure the transmittance through this arrangement of particles, we get a curve like this. And so here in this graph, the vertical axis is logarithmic, so an exponential curve will be a straight line. And indeed, for the case of independent particles, the line is straight. Now, for the case of particles that repel each other, or this kind of blue noise distribution, we get a curve like this. And so we can see it is a straight line, so it is indeed an exponential, but it has a steeper slope than if we assumed the particles were independent. So clearly, the properties seem to change depending on the particle arrangement. So finally, for the case of these cloud particles or distributions of these large voids and clusters, we get a curve like this that quite significantly deviates from an exponential. It has a much longer tail than predicted by classical transport theory. All right, so I've made the case that there is correlation between particles and reality, and this correlation does matter. It does affect transmittance. And so the next question is, why don't we just render with non-exponential transmittances? And so here I'm showing the classical rendering equation for participating media. It consists of two parts. The first one describing the transport from a surface to another surface, and the second part describing the transport from the medium to a surface point. And we can see that in both of these terms, there appears a transmittance. Of course, in classical transport, we simply assume this to be an exponential. But of course, nothing stops us from inserting a curve other than an exponential into these terms. And so to show what happens, I have a little experiment here, where on the left-hand side, I have a simple scene, a kernel box that's filled with a participating medium. And here I'm rendering it with a classical exponential transmittance. So now if we insert this, say, transmittance we obtained from the cloud model, and we rendered the same scene with it, we get an image like this. And so clearly this doesn't look right. It's much brighter. And in fact, if we let this keep running, then eventually the image values explode towards infinity. And this is because the image actually gains energy, or more energy comes out of the medium than goes into it. So clearly something is wrong. Inserting a non-exponential transmittance seems to have violated something fundamental about this equation. So this is not the way forward. All right, so what did I just talk about? Well, I've shown that classical transport assumes that particles are independent. And I've shown that this model isn't necessarily accurate to real media. And whenever we allow for correlations between particles, we get a non-exponential transmittance. And clearly, this non-exponential transmittance breaks classical transport. We get images that don't make sense. And so ultimately, this means that we need a new transport framework that can accommodate non-exponential transmittances so that we can render these correlated media. Now going back to this rendering equation, we can see that in the right-hand term, we have this thing called the scattering coefficient. And it turns out this scattering coefficient is actually two terms in disguise, something that we call the extinction coefficient and the albedo. Now, we usually write the equation in terms of transmittance and scattering coefficient because it's quite convenient for rendering. But truly, if this transmittance is an exponential, then we can regroup this equation in a different way. In fact, this exponential times the extinction coefficient is a different function altogether. It's something that we call the free flight PDF. And now I haven't changed anything about this equation. I've simply rearranged terms, but now we can reinterpret it in a way that's more useful. And in fact, in this equation, before we had two transmittances, and now there is a transmittance in a free flight PDF. We have two different functions that fundamentally describe two different events. One describes transport from a surface to another surface, and the other describes transport from a surface to the medium. So we can immediately see that there's actually two other types of transport that are possible. We could have transport from the medium to a surface, and transport from a point in the medium, or a particle, to another particle. Now, in classical transport, this distinction doesn't matter. The transport functions would be an exponential in all of these cases. And this is why it doesn't matter that we write the rendering equation in terms of two transmittances instead of a transmittance in a free flight PDF. However, if we allow the transmittance to be non-exponential, or in other words, if we allow the particles to be correlated, then each of these transport cases is represented by a different transport function. So we actually end up with 4 different transport functions that describe events in media. And so you have abbreviated them with 2 letters that describe the location of the endpoints of the segment. So if the point is in the medium or in a particle, we abbreviate it with P. If it's on a surface, or in other words, in free space, it's not limited to a particle position, we say this point is an F. And so FF would be surface-to-surface transport, and so forth. Now these 4 functions have quite intuitive interpretations. And so namely, any function that ends in F is a transmittance. It ends on a surface. It represents a proper transmittance. And in other words, this is a probability. And so there's a function that starts at 1 and then decreases with distance. And this is the probability that we'll fly through a certain distance through the medium without interacting with it, without colliding with a particle. Now, any function that ends in P, on the other hand, is a free flight PDF. This is a probability density. It integrates to 1. And this is simply the probability density that we will interact with a particle after traveling a specific distance through the medium. Now, it seems daunting that now, instead of one function, the transmittance, we have these 4 different transport functions. And so we might wonder, how do we represent these? How do we obtain these 4 different functions? But it turns out it's a lot easier than that, because in the paper we can show that these functions are tightly related to each other. In particular, we can relate the free flight PDF to the transmittance through integration. And we can also go the other way from the transmittance to the free flight PDF through differentiation. We also show that the surface to medium and the medium to surface transport functions are actually the same function, simply scaled differently, scaled by a constant factor that we call sigma bar, which is the average density in the medium. And so in other words, all of these functions are very tightly related to each other, and if we have any one of them, we can derive all the others through differentiation or scaling or integration. Now, for more convenience, we wrap these transport functions into something that we call the transport kernel, which is simply a big case statement that selects the appropriate function based on the location of the endpoints. If one endpoint is on the surface, the other in the medium, then we pick PF and so forth. And so the only change that we need in the end to convert the classical rendering equation into one that supports non-exponential media is that we take the transmittance, or the transmittance times the scattering coefficient, and replace them with the transport kernel. And so now we select the appropriate transport function for each type of event instead of always using the transmittance. And so in this talk, I've only shown you how to modify the rendering equation. In the paper, we do the whole derivation in terms of the path integral, which allows us to show all kinds of useful properties that this has. In other words, this is a reciprocal equation. It's energy conserving, all the good things that you would want in a renderer. And so to summarize what I've just talked about, I've shown you that in correlated media, the transmittance actually becomes 4 different functions that represent different types of interactions at the endpoint. And so for uncorrelated media, this didn't matter because all 4 functions are an exponential, but in the non-exponential case, these are very different. And so we do need to make the distinction to get correct renderings. I've also shown that these functions are not arbitrary. They're very tightly related to each other. And if we have any one of them, we can derive all the others from it. And I've only given a very high-level abstract overview in this talk, simply due to time constraints. But in the paper, we do have a rigorous mathematical derivation that actually shows that all of this is true and correct. All right, so now we know how to render with non-exponential transmittances. But the next problem is, how do we obtain these transmittance curves? And This is very analogous to surface rendering or obtaining BRDFs or surface scattering functions in that fundamentally there's three different ways of doing it. The first way is the data-driven approach, where we either physically measure real materials and record their transmittances, or we represent materials virtually and then do virtual measurements and tabulate the results. And this is what I've shown you at the beginning, where we've actually instantiated different types of particle distributions and then measured in the computer the transmittance through these particles. And these curves we could tabulate, we could use them in our renderer. And in a way, this is the gold standard of obtaining transmittance curves, because it can handle any type of particle distribution, and for any transmittance, there is an actual real distribution of scatterers that has this transmittance. Unfortunately, this is also quite expensive. Doing these experiments and simulations is quite time-consuming, and also once we've done the measurement and we've obtained the curve, then it's fixed. We can't go back and change the parameters of the medium without having to redo the simulation. Now, the complete opposite end of the spectrum is the phenomenological approach to obtaining these appearance models or transmittances, where we simply come up with a formula for the transmittance, or say for the BRDF, and then insert it into the computer and see if it produces a useful result. And this has been done for materials. One great example is the Fung shading model. But we could also do this for the transmittance and simply come up with a formula that kind of produces an interesting result. Now, finally, between the data-driven and the phenomenological approach is the realm of statistical models. And for this case, we come up with a model for how the scatterers are distributed, and do this in a way where we can derive in closed form the transmittance of this particular distribution of scatterers. So in a way, it has the same properties as the data-driven approach in that each transmittance curve corresponds to an actual distribution of scatterers, except these curves we can parameterize because the model has some parameters, and hopefully the curve we derived in closed form allows for inserting these parameters also. And there's different ways we could do this, and one way that's particularly useful is that we can kind of view a medium as a fractal, or in other words, it is the sum of different amplitudes and frequencies of noise. And by varying the amount of noise and the frequency spectrum and the amplitude spectrum, we can get quite different results. And the nice thing about these noise functions is that we can apply powerful mathematical tools to derive the transmittances in closed form. And this is something that was done by Davis and Manif Weinstein, who derived the transmittance curves analytically for different frequency distributions of noise. And this allows them to get quite different types of media, but still get the transmittances for these media in closed form. And so we import this work into graphics and also show some related approaches for obtaining analytic transmittance curves. So I've shown you how to obtain transmittance curves and how to insert them into the rendering equation. And now I'll show you what this actually looks like. And so I'll show two examples. The first showing phenomenological transmittance. In other words, this is a non-physical model where we've simply come up with interesting formulas that produce interesting results. And so here on the left-hand side, I'm showing you a simple scene containing a scattering medium, and this is rendered with an exponential transmittance curve, so assuming independent scatterers. On the right-hand side, I'll show you the same scene but rendered with curves that we've come up with. And so if we use a step function for the transmittance, we get the appearance of almost a sphere of light surrounding the light source. A linear falloff produces a simpler appearance, but with a feathered kind of edge. If we used a step function, then we get an image that almost looks like there are spheres or shells of light surrounding the light source. And finally, we also tried using a sum of two exponentials with different coefficients, and this produces an interesting result where we have this clustering of light around the light source, but also a long fall-off, where we still get this kind of sheen off of surfaces in the scene. And so in the following, I'm showing you a porcelain dragon which is rendered with different types of non-exponential transmittances. And so I'm interpolating between different types of phenomenological curves. And that shows you the change in appearance as we go through different types of curves. You can see that the appearance of the dragon changes quite drastically, but we haven't changed anything about the media properties other than the transmittance. And so this kind of shows you that we can unlock a whole new space of appearance simply through modifying this transmittance curve. Now finally, I will show you a rendering of a cloud rendered with a physically based model derived from Davis and Manif-Weinstein model. And here in the top left, I'm showing you the parameter space of this transmittance curve. We can control the amplitude and the frequency of the noise. And in the top right, I'm showing you the resulting transmittance curve. And so here I'm simply linearly interpolating between points in this parameter space. We can see the transmittance curve changes quite a bit, and also the appearance of the medium changes quite dramatically, ranging from soft to harsh, and from light penetrating deep into the medium to light scattering quite at shallow depths. So I've talked quite a bit about solutions, but of course our work also has some limitations. Primarily, our work assumes that we have the same correlations everywhere in the medium. So we cannot handle a medium that, say, half of it follows a type of blue noise distribution and the other half follows a distribution that we would see in clouds. Additionally, although we support heterogeneous media, we do not support unbiased distance sampling methods for heterogeneous media. Methods such as delta tracking or Woodcock tracking rely on the fact that the transmittance is an exponential, and this breaks down when we try to insert non-exponential transmittances. And so we're limited to ray marching or regular tracking. Now for future work, now that we have this tool of non-exponential media, we'd like to apply it to different use cases. For example, we could use it as a tool for approximating multiple scattering. This is something that's already been done in the movie industry, where people use exponentials with different coefficients for primary rays and secondary rays, and this kind of approximates light penetrating deeper on indirect bounces due to multiple scattering without actually having to trace this many paths. And now with our framework, we could do the same thing, but in a more principled approach and kind of insert more interesting curves to broaden this space of appearances. Finally, we'd also like to apply this to do level of detail for participating media. So sometimes we would like to use a lower resolution version of a heterogeneous medium, for example, because it's far away. But if we simply average the densities within each cell, we get quite a large appearance change. This is because averaging the densities is not the same as averaging the transmittances. And in fact, if we do this downscaling, then we end up with a non-exponential transmittance curve within each grid cell. And so again, we could use our tool of non-exponential rendering to handle these cases more accurately. Finally, now that we have a better idea of what our work does, we're in a better position to compare it to previous work. Now, the work of Davis and Manif-Weinstein also looks at correlated scatterers, but they only introduce a non-exponential transmittance curve and don't come up with a new radiative transfer equation. On the other hand, the work of Larson and Vasquez in neutron transport, and also more recently in graphics, the work of Hirabo et al., both introduce new non-exponential rendering equations. And it's useful to point out the differences and similarities between these approaches. So both our work and that of Hirabo et al. Explicitly incorporate surfaces in the transport equation, whereas the work of Larson and Vasquez does not, because in neutron transport, surfaces are not nearly as important as they are in graphics. Now, our work is the only one that supports heterogeneity, which again is quite important in graphics to render things such as clouds or skin. Our work and that of Larson and Vasquez takes great care to ensure that the resulting transport equations are reciprocal, which is important for bidirectional rendering, but Hirabo et al. Do not. Finally, we're the only ones to explicitly introduce a non-exponential path integral, which again is important to apply different types of rendering algorithms, such as photon mapping or bidirectional path tracing. So I've reached the end of this talk. Thank you very much for your attention. And I'm finally showing another cloud rendering, flipping back and forth between the classical exponential rendering equation and a transmittance curve derived from pink noise.